What I want to do in this video is give ourselves a basic introduction to the phenomenon of light. And light is, at least to me, it is mysterious because on one level it really defines our reality. It's maybe the most defining characteristic of our reality. Everything we see, how we perceive reality, is based on light bouncing off of objects or bending around objects or diffracting around objects and then being sensed by our eyes and then sending signals into our brain that create models of the world we see around us. So it really is almost a defining characteristic of our reality. But at the same time, when you really go down to experiment and observe with light, it starts to have a bunch of mysterious properties, and to a large degree it is not fully understood yet. And probably the most amazing thing about light, well, actually there's tons of amazing things about light, but one of the mysterious things is when you really get down to it, and this is actually not just true of light, this is actually true of almost anything once you get onto a small enough quantum mechanical level, but light behaves as both a wave and a particle. And this is probably not that intuitive to you because it's not that intuitive to me. In my life, I'm used to certain things behaving as waves, like sound waves or the waves of an ocean. And I'm used to certain things behaving like particles, like basketballs or I don't know, my coffee cup. I'm not used to things behaving as both. And it really depends on what experiment you run and how you observe the light. So when you observe it as a particle, and this comes out of Einstein's work with the photoelectric effect, and I won't go into the details here, maybe in a future video when we start thinking about quantum mechanics, you can view light as a train of particles, of particles moving at the speed of light, which I'll talk about in a second. And we call these particles photons. If you view light in other ways, and you see it even when you see light being refracted by a prism here, it looks like it is a wave. It looks like it is a wave, and it has the properties of a wave. It has a frequency, and it has a wavelength. And like other waves, the velocity of that wave is the frequency times its wavelength. Now, even if you ignore this particle aspect of light, if you just look at the wave aspect of the light, it's still fascinating because most waves require a medium to travel through. So for example, if I think about how sound travels through air, so let me draw a bunch of air particles right here. I'll draw a sound wave traveling through the air particles. What happens in a sound wave is you compress some of the air particles, and those compress the ones next to them. And so you have points in the air that have higher, I guess you could say higher pressure, and points that have lower pressure. And you can plot that. So we have high pressure over here. High pressure, low pressure, high pressure, low pressure. And as these things bump into each other, and this wave essentially travels to the right, and if you were to plot that, you would see this waveform traveling to the right. But this is all predicated, or this is all based on this energy traveling through a medium. And I'm used to visualizing waves in that way. But light needs no medium. Light needs no medium. It needs no medium. Light will actually travel fastest through nothing, through a vacuum. And it'll travel at an unimaginably fast speed. 3 times 10 to the 8th meters per second. And just to give you a sense of this is 300 million meters per second. Or another way of thinking about it is, it would take light less than a seventh of a second to travel around the Earth, or it would travel around the Earth more than 7 times in 1 second. So unimaginably fast. And not only is this just a super fast rate, and this is a super fast speed, but once again, it tells us that light is something fundamental to our universe, because it's not just an unimaginable fast speed. It is the fastest speed, not just known to physics, but possible in physics. So once again, something very unintuitive to us in our everyday realm. We always imagine that, okay, if something is going at some speed, maybe if there was an ant riding on top of that something, when it was moving in the same direction, it would be going even faster. But nothing can go faster than the speed of light. It's absolutely impossible based on our current understanding of physics. So it's not just a fast speed, it is the fastest speed. It is the fastest speed possible. Fastest speed possible. And this right here is an approximation. It's actually 290, well, it's 2.99 something something times 10 to the 8th meters per second. But 3 times 10 to the 8th meters per second is a pretty good approximation. Now, within the visible light spectrum, and I'll talk about what's beyond the visible light spectrum in a second, you're probably familiar with the colors. Maybe you imagine them as the colors of the rainbow. And rainbows really happen because the light from the sun, the white light, is being refracted by these little water particles. And you can see that in maybe a clearer way when you see light being refracted by a prism right over here. And the different wavelengths of light, so white light contains all of the visible wavelengths, but the different wavelengths get refracted differently by a prism. So in this case, the higher frequency wavelengths, the violet and the blue, gets refracted more. It gets bent, its direction gets bent more than the low frequency wavelengths, than the reds and the oranges. Than the reds and the oranges right over here. And if you want to look at the wavelength of light, they're a visible light. It's between 400 nanometers and 700 nanometers. And the higher the frequency, the higher the energy of that light. And that actually goes into when you start talking about the quantum mechanics of it. That the higher frequency means that each of these photons have higher energy. They have a better ability to give kinetic energy to knock off electrons or whatever else they need to do. So higher frequency, let me write that down. Higher frequency means higher energy. Higher energy. Now, I keep referring to this idea of the visible light. And you might say, what is beyond visible light? And what you'll find is that light is just part of a much broader phenomenon, and it's just the part that we happen to observe. And if we want to broaden the discussion a little bit, light is just, or I should say visible light, is just really part of the electromagnetic spectrum. So light is really just electromagnetic radiation. Magnetic radiation. And everything that I told you about light just now, it has a wave property and it has particle properties. This is not just specific to visible light. This is true of all of electromagnetic radiation. So at very low frequencies or very long wavelengths, we're talking about things like radio waves, the things that allow a radio to reach your car, the things that allow your cell phone to communicate with cell towers. Microwaves, the things that start vibrating water molecules in your food so that they heat up. Infrared, which is what our body releases, and that's why you can detect people through walls with infrared cameras. Visible light, ultraviolet light, the UV light coming from the sun that'll give you sunburn. X-rays, the radiation that allows us to see through the soft material and just visualize the bones. Gamma rays, the super high energy that comes from quasars and other certain types of physical phenomena. These are all examples of the exact same thing. We just happen to perceive certain frequencies of this as visible light. And you might say, hey, Sal, how come we only perceive certain frequencies of this? How come we only see these frequencies? And I'll put these. Literally, we can see those frequencies with our unaided eye. And the reason, or at least my best guess of the reason of that, is that's the frequency where the sun dumps out a lot of electromagnetic radiation. So it's inundating the Earth, and if, as a species, you wanted to observe things based on reflected energy, a reflected electromagnetic energy, it is most useful to be able to perceive the things where there is the most electromagnetic radiation. So it is possible that in other realities or other planets, there are species that perceive more in the ultraviolet range or on the infrared range. And even on Earth, there are some that perform better at either end of the range. But we see really well in the part of the spectrum where the sun just happens to dump a lot of radiation on us. Now I'll leave you there. I think that's a pretty good overview of light. And if any of this stuff seems kind of unintuitive or daunting or really on some level confusing, this wave-particle duality, this idea of a transfer of energy through nothing, and it seems unintuitive, don't worry. It seems unintuitive even for the best of physicists. So you're already at the leading edge of physics thinking.